minutes have passed now. Once again, a warm welcome from my side to our special session called Integrated Logistics Planning for Efficient Smart Manufacturing. What you just heard in German language was the talking between us concerning how we would best share the screens and do concerning the time limits. But now we've fixed all issues, and so we would like to officially start. It is a pleasure that we have here 3 speakers. Absolutely excellent in their respective fields, and we start with Margaretha Gansterer. She is university professor and head of the Institute for Production, Energy and Environmental Management at the University of Klagenfurt, and so please, the stage is yours.
Yeah, thank you for the nice introduction and for the invitation. So I was invited to give a talk on shared resources in collaborative vehicle routing, and the stuff that I'm presenting today is a joint work with Richard Hartl from the University of Vienna. So if we think about transportation in the sharing economy, I think almost everybody has the same ideas in mind. So the sharing economy in connection with transportation brings us to Uber, of course, to bike sharing like Lime Bike, or car sharing like Car2Go, or we might think about crowd delivery. Recently, there is a lot of stuff going on in the field of crowd delivery. So where we have like occasional drivers who do deliveries to persons who cannot or who are not able to like, for example, enter grocery stores. So we have crowd delivery services, or here on the left lower corner of the slide, you see locker boxes. Also, locker boxes are like shared delivery spaces. If we want to get if we want to reduce the cost in the last mile delivery, we are thinking about locker boxes where different companies can share this resource and deliver like packages to these locker boxes. And also this is related to sharing economy in transportation. But in a more narrow sense, if we talk about transportation in the sharing economy, typically we talk about collaborations. So if we have companies who really offer their idle capacities to competitors. So this is why we call it horizontal collaboration. So we have, like here on the picture, we have different delivery companies. And as we all know, the last mile delivery is very inefficient. So we have a lot of delivery companies in our cities or in our urban areas delivering or having strongly overlapping delivery routes, and this is why the field of horizontal collaborations, in order to get rid of these inefficiencies. So we have a lot of delivery companies who have idle capacities, and the question is, how can we encourage them or maybe force them to join their forces to, like, for example, exchange idle capacities in order to get more or to increase efficiency and to reduce costs. And so with these collaborations, we are aiming for economic and for ecological goals, because we do not only reduce inefficiencies and do not only reduce costs, but of course we also aim for less congestions, less emissions of harmful substances in our urban areas. So if we talk about horizontal collaborations, it is like companies who are basically in a competitive setting. So they are typically not business partners, they are competitors, but still they are willing to. They are either willing or they are forced by public authorities to share their idle capacities in order to make our cities more environmentally friendly. Okay, so just a very a picture just to very simplistic picture of the setting. So let's think about carriers. They are delivering parcels, for example, in cities. And this is the situation that we observe in many cities, including Vienna, is that we have different trucks running through our city and serving customers. And we have all these overlapping tours that we can see here. So we have a red carrier and a blue one and a green one, and they have strongly overlapping tours. And this is, of course, inefficient, and it leads to harmful or to damaging situations for our environment. So what techniques can we apply in order to aim for this situation that we see here? You see that all the customers that were served previously are still served, of course. So everybody is delivered by a truck or a carrier, but we do not have any overlapping tours, and we have, of course, more efficient routes here and an ecological improved situation. So what you find in the literature are basically two streams of research in this setting of collaborations. So we have one stream on centralized collaborations and one stream on decentralized collaborations. So if we talk about centralized collaborations, we assume that there is one central decision maker, like a digital platform, who is fully informed. So the central decision maker has full information about all the transportation requests that have to be served, and assigns transportation requests to carriers. Okay, so these are centralized collaborations. There is some neutral authority having full information and doing like an assignment problem and maybe also a routing problem, and decides which customer is served by which truck, and ensures that there are no overlaps, or that we find the best solution without overlaps and still minimizes transportation costs. So these are centralized collaborations. Obviously, if we have one single decision maker having full information, then we have like a classical routing problem where we have to assign requests to carriers and then decide on the sequence of serving these customers. And the second stream, if we assume that there is no fully informed decision maker, because maybe these carriers, they are willing to enter collaborations, but they are not willing to reveal all the information, then we have decentralized collaborations. Decentralized collaborations indicates that carriers are willing to, for example, exchange the transportation requests, but they want to have hidden information. They do not want to reveal all the information, so they might be willing to do bilateral exchanges or to perform some kind of auction mechanism where they have some mid-biddings and in order to reach good solutions, but they are not willing to give all their information, like all their costs and all their customers, to a platform or to a central authority. Okay, so these are the two streams of research, and in my talk I want to give you a bit of insights on the state of the art for both of these streams. So what are barriers for these collaborations, particularly for the centralized collaborations? We have a lot of barriers. One of them I already mentioned, which is that information released to competitors. So we need a high level of trust, because if you are willing to enter a centralized collaboration, you have to fully trust the other competitors and also the central authority, the digital platform, because you have to put a lot of information to this setting. Apart from this problem of trust, of course, data security is a problem, because if you have some data leaks, if sensitive information is revealed, then nobody will be willing to enter such a collaboration. Computational complexity. So if you're in the field of routing problems, you know that decisions for only one carrier are already quite complex and computationally challenging. But if you have a platform where several carriers put all their requests onto this platform, and this platform has to solve a routing problem for all these carriers, assignment and routing problem, then of course you run into some computational complexity. What is mentioned in the literature and what we also hear from practitioners is that carriers typically have something like key customers that they do not want to offer to their competitors, even if they are willing to share information and willing to collaborate with them. They have some customers because they have very strong relationships with them, or they are highly valuable. So they have key customers that they want to keep for themselves. Then there are typically consistency problems, that customers want to be served by not by 3 different carriers, but they want to be served always by the same carriers. So this is service consistency. We might also observe time consistency. These customers will want to be served always at the same point in time. Then we have legal aspects, thinking about antitrust laws, but I'm not a legal expert, so but it seems that from this perspective, these collaborations are okay, but I do not want to dig too deep into this because it's not my expertise. And then we have profit sharing issues, like if we have this collaboration, and of course this collaboration will make some profit because we reduce costs. Then the question arises, how do we share these profits? So there are several different profit sharing mechanisms that we could apply, and of course fairness issues. Nobody wants to enter a collaboration ending up with only very few customers while other competitors are having full routes. So we have fairness aspects that we have to consider to ensure that there is well-balanced workload, for example, and that everybody can trust into this collaboration. Okay, as I said, if we have centralized collaborations, we have a classical optimization problem, quite challenging because typically we have a lot of carriers working on these platforms. And so together with Richard Hartl, I did some observations on how these barriers that I mentioned might affect these collaborations. So, for example, we showed that keeping key customers is not an issue. We can find very good solutions, very close to the optimal solution, by even if carriers are insisting on their key customers. Also, minimum profits, we could show that minimum profits could easily be kept for each carrier. So this is this fairness aspect. What I recently showed together with Richard Hartl and my postdoc Simona Mancini, we investigated whether time consistency and service consistency is an issue. So whether it decreases our solution quality if we have customers insisting to be served on the same period, on the same point in time on all days. This is time consistency, and also if we have customers who insist that they are always served by the same carrier and are not served by different carriers. So this is what we call service consistency and time consistency. So we are entering a multi-period setting, obviously. So we assume that carriers have to serve customers on a periodic setting, and in this setting we also investigate whether fairness can be kept, so like a fair workload balance between the carriers. So for this problem we formulated the mathematical model and introduced an efficient solution approach. Very briefly on the mathematical model, so we have carriers, customers and periods, and the objective function that we have maximizes the total profit of all collaborating carriers. So we have the revenues and we have the costs of serving customers. This is what we have in the objective function. Then we have assignments. So this is what we need for the service consistency. So we have to ensure that each customer is served, and if we have service consistency, that each customer is served by exactly the same carrier over the whole planning horizon. Then we have the number of vehicles, which is limited. This is quite straightforward. We have time and time consistency. So if there are customers who want to be served at the same point in time every day. Then we have load capacities. Vehicles have restricted amount of load, of course. And finally, we have the consistency and the final profit. So this indicates that we have like a minimum profit that each carrier has to have in this collaboration, and this minimum profit depends on the initial profit. So if a carrier enters the collaboration, this carrier has like a benchmark. This is the initial profit or the initial number of customers this carrier is serving, and we have to ensure that there is a certain threshold that we have to keep. So in order to ensure that these carriers are still willing to stay in this collaboration and not leave because they have the impression that they are just losing in this collaboration. So these are these two constraints, 16 and 17. In order to speed up the solution procedure, we introduced some valid inequalities. So I will not go into details, but we have to ensure that the revenue of each carrier is higher than the initial profit. This is here in the first valid inequality. Then we have sufficient capacity if we assign customers to carriers. We ensure in one of these valid inequalities that the customers that are newly assigned to a carrier do not exceed the maximum amount of customers that have been given up by some of the competitors. And then we have a bound for the number of active arcs. So very briefly, no details on the model, just that you have an impression what we are solving here. We have three different solution approaches. So we tried to solve it to optimality by a commercial solver. Then we have, which we succeeded for quite small instances with 20 customers, 4 carriers in 4 periods. Then we have a mathuristic approach based on large neighborhood search, and an iterated local search, which is again based on this on our mathuristic. For the mathuristic, we use the initial assignment of customers to carriers as a starting solution. Then we do a local search, which is the solving the optimal problem by fixing some of the carrier customer assignments and loosening the other ones. And then we re-optimize all pairs of carriers and try to find a better solution. If we find a better solution, we restart the procedure, and we repeat this until we do not find an improvement anymore. So this is how it looks like. So let's assume a very simple example where we have carriers. We have to have in mind that we have pickup and delivery requests. So here on this simplistic illustration, I just have pickup or delivery requests. So we have this initial assignment, green, blue, and red customers. So we fix the red customers, and the green and the blue ones are re-optimized. And then so we have a new assignment of customers to carriers and new routes. And the next step, we fix the green one, and in the next step, we fix the blue one. And this is how we iterate through all the procedure until we do not find an optimal and an improved solution anymore. For the iterated local search, we do the same with just perturbation step. So whenever we converge to a solution with the mathuristic, we do a perturbation steps of customers, we newly assign them, and then we again start this mathuristic. Okay. We investigated several instances which we adapted from Vidal in the literature to the setting that we have here. So multi-periods, 20 and 50 customers, 49 and 150 visits, 4 or 6 periods, 4 or 8 carriers. We did several computational studies. So first of all, we evaluated the valid inequalities. We benchmarked our solution approaches, and then we derived some very interesting and surprising managerial insights. So this just for the valid inequalities, we could show that the combination of 20, 22, and 23 performed best. So all the valid inequalities did their job, so they improved the solution approach, but the best, we tested all possible combination, and this was the best combination that we found. For the benchmarking, we could show that the mathuristic on the small instances outperformed the other approaches, and on the large instances, the iterated local search was a bit better because it's only slightly more computational time, but the solution quality was better. So all the remaining so all the computational results for the managerial insights were performed using the iterated local search approach. So what we found was, first of all, that all the requirements that are mentioned in the literature, so this is like having a fair allocation, having key customers, having time consistency, and having service consistency, come for free. This was quite nice to see. Whenever we introduced these, whatever of these constraints that we introduced, we only, for many instances, we had the same solution. We had the same solution quality, the same optimal value. But for even if we introduced like workload balance, service consistency, time consistency, so there was no reduction in solution quality. But so this is very nice to see. It supports somehow other findings that we already had in the previous study, but for the one period problem. But in this study, we could show that for multiple periods, we can also introduce all these constraints and do not have a gap in solution quality or a decrease in solution quality. One very interesting finding was that if we assume fair profits in the sense that, or fair workload in the sense that after the planning horizon, no carrier should have less profits than before the carrier enters the collaboration. This is very easy. It comes for free, as I said, almost for free. But what is really, really expensive for the collaborations is if we assume that daily profits have to be kept. So each carrier on each day in this planning horizon has to have at least the same profit as before. This is extremely expensive. In most of the instances, we did not find any feasible solution. So this was a very interesting setting, that it is no problem to keep in the whole planning horizon, but it is extremely costly if we assume that each carrier wants to have the same profit for each day. So this is a very interesting finding for multi-period collaborations, and this have to be kept in mind. So in the last 2 minutes, I just want, so if you think that decentralized collaborations, they are nice, but maybe they are not practically relevant because there are not too many carriers who are willing to enter such a collaboration where they have to put all their information, then you come into decentralized collaboration. So you have like, for example, bilateral exchanges, or as we show in one of our papers, that combinatorial auctions are a very strong method here. So we have an auction mechanism where carriers can put their requests into a pool, and their requests are like bundled to packages and then offered to competitors. So there is almost no information have to be revealed to their competitors, and information has to be revealed to the auction authority. And we could show that these mechanisms also work very well and find very good solutions. So this sounds like a very strong tool. You just have to have in mind that they are still even more complex than solving the centralized problem. So you run through 5 quite complicated phases here. So first of all, these carriers, they have to decide which customers they want to reveal to their competitors, which they want to submit to this auction pool. So you have to solve NP-hard routing problems in order to decide which of the requests am I willing to offer. Then you have like a bundling where the auction mechanism has to find good, valuable, attractive packages that are offered to the participants. This is also a very complex task because you have 2 to the power of n-1 possibilities to produce bundles out of n requests. Then you have some kind of bidding where carriers give their bids on bundles of requests that are offered. So again, you have to solve routing problems. And then you have a winner determination, which is typically formulated as a set partitioning problem, where the best combination of packages to carriers is to be found. And finally, again, you run into profit sharing. So whenever you are tackling collaborations or collaborative problems, you have the issue of profit sharing. So how can the profits that we generate be shared fair among these participants, such that we have like stable collaboration. So you run through several phases, and so this is just to show that even if you decide that decentralized collaborations are more practically relevant, you have some complexity issues here. So from game theoretic perspective, you have to ensure that you have an efficient solution approach in order to find good solutions, which we could show it is possible. You have individual rationality, so that each carrier, each participant has no reason to leave the collaboration. So this is what is called individual rationality. You have some kind of budget balance, which relates to the profits that you make. And you have incentive compatibility, which has to ensure that, ensures that carriers who participate in the collaboration do not have to deviate from the jointly agreed strategy. So this is what we call incentive compatibility, like giving the real bid prices, for example. So they should not have incentives to cheat on the bids that they give. Otherwise, you will not be able to have an efficient mechanism. Okay, and with this, I'm at the end of my presentation, and I'm happy to answer questions.
Okay, thank you, Margaretha, for this very nice and interesting talk. Are there any questions from the audience? Please feel free just to raise your hand or unmute your microphone and go ahead and ask.
Can I?
Of course, please.
So you have been working on consistency aspects. So the question is, now you do time consistency. What about the driver consistency aspect? Because as soon as you do collaboration, probably it's not always the best option to have the same company visit the same customer, because otherwise you would not maybe trade the customer. Is it, or is this not an issue? Because I would expect that this can be an issue in a way.
You mean that, so what we consider is time consistency, of course, and service consistency, but service consistency only in the sense that the same company is serving the customer. We thought about including driver consistency, but then we decided, okay, if in this setting it might be enough, and this is what we got from practitioners, that they said customers, they want to be served by the same company. They do not want to have on one day DHL and on the other, and the next day they want to have UPS. They want to have one single company, and yeah, maybe including driver consistency would be worthwhile as well, but we did not do this so far.
So this maybe then on a company level that they then try to use.
Yeah.
Okay.
Yeah.
Okay, thank you. Any further questions? If not, actually, I would have one. What is your experience? You just said that, of course, you talk to practitioners. What is your experience when talking to companies for which this could be interesting? Do you feel that the interest is higher than the fears, the barriers, or vice versa? And if the barriers are, like you said at the beginning, there are several possible barriers, how could they be overcome?
I think this depends. So what we observed is for last mile delivery companies, they are quite interested in this and willing to use it. Maybe because they are really observing their inefficiencies, and also because I think at least in Vienna there are a lot of discussions that this might be somehow mandatory at some point, because we have too much congestions. And also they observe that last mile delivery is extremely expensive, and so if they see that they can really have a profit from entering these collaborations, they are willing to overcome these barriers. In long haul transportation, it is much more complicated, because the long haul transport carriers, they know if they put a request on the platform, everybody knows, okay, this is the customer, because they see the final destination and they see where the product is coming from. So I think they are more reluctant to enter these collaborations. I think there's more potential in last mile delivery, because there is so much cost pressure on these companies And I think at some point they will be willing to enter these collaborations.
Okay, thank you very much. Are there any more questions now? So if not, Margaretha, Gansterer, once more, thank you very much for this very interesting talk. I would like to now introduce the second talk, which is given by Sophie Parragh, who is Professor for Production Logistics Management and Head of the Institute of Production Logistics Management at the Johannes Kepler University in Linz Business School. Please.
Okay, thank you very much for the introduction. I will now try to share my screen. I hope it works now. So again, thank you very much for the introduction, and thank you also for the invitation to give this talk. Those who know me, they could immediately guess that it will be on bio multi-objective optimization, because this is one of our main research fields, together with optimization in logistics. And that's also where the title of my talk comes from. So the title is Integrated Logistics Planning, a Bio-Objective Optimization Perspective. And I will try to convince all of you that bio-objective optimization is something you should also consider in dealing with integrated logistics planning problems. Okay, so first of all, the work I'm going to present is, of course, not only my own work, but it is work that I have done jointly over the past years with Fabien Tricoire, Walter Gutjahr, Miriam Enzi, and also Jakob Buchinger. But what's the motivation? So the motivation for talking about this is that, in my opinion, integrating more layers, aspects, and as well as perspectives into optimization problems does not always result in a new complex problem, but it very often gives rise to more than one objective. So if you combine two problems, usually they have their own objective functions, and if you combine them, then you have two objective functions, and very often these two objective functions may not be easily combined in a meaningful way for decision makers. And that's why I want to today convince you that you should keep these objectives at least initially separate in order to understand their trade-off relationship. So that gives me also the second point already. So I believe that we all believe that there are a lot of objectives which are in a trade-off relationship. That means if you optimize one, it will deteriorate the other. And this implies that at some point you have to decide if you want to emphasize more this one objective or the other objective, or you want to find maybe a solution in the middle. But without revealing the trade-off between these different objectives, you are kind of left in the dark on what this trade-off relationship is. And our focus here is to develop efficient methods that are able to produce trade-off solutions where decision maker in the end can then choose the most suitable solution out of this set of. Okay, and here are some examples we've been working on. For example, since today is Sustainability Week, I will start with the sustainability-oriented problem. We have been working, for example, on a green city hub location problem where we applied our kind of generic methods to, where we have on the one hand the hub opening costs. That means we want to open hubs at the city borders or closer to the city center, and then have the distribution from these hubs. And then we had as the second objective to minimize the long-term CO2 emissions. So when we open the hubs, we do not only want to consider what the costs of the hubs, but on the other hand also what is the impact, or what are the total CO2 emissions depending on where the hubs are located and what kind of fleet composition is used at the different hubs. The second example has kind of a COVID-19 relationship, and this is also the problem I will use in order to illustrate the methods we have developed. It's motivated originally from disaster relief logistics. However, unfortunately, at the moment, we are kind of also facing, let's say, a crisis, not a disaster, but it's kind of a disaster, because we are living in very strange circumstances due to the COVID-19 pandemic. And the problem we have been dealing with already over the past years is coming from disaster relief logistics, where we try to determine the local distribution centers for relief goods. And if you now make the COVID-19 connection, it could be a place where COVID-19 testing stations are located. So there's a strong connection to also the pandemic we are living through at the moment. The third example we've been working on, that I will also briefly use to explain an alternative option on how to compute trade-off solutions, is car sharing. So this is very much related to the first talk. It doesn't concern sharing in the sense that you want to share packages or orders that you want to redistribute among carriers, but car sharing is more about persons sharing vehicles. And in this case, it's also important to consider user preferences when implementing such a system, for example, within a company. So there's the idea that companies could move from company-owned and assigned cars to individual persons to more of a carpool type setting. And in this case, it's not only the costs which play a role, but it's also user preferences, and they have to be taken into consideration. And this is what we do when we look at this problem. And the fourth example I'm showing now is the profitable tour problem, which is again related to the routing you have seen before. But here it's more that you decide on which customers you visit based on the profits, and this is very closely linked to this sharing problem that you have seen in the previous talk. And here what we looked at from a multi-objective or bi-objective perspective was to optimize costs on the one hand and scores or profits for visiting a customer on the other hand. And then you also see a nice trade-off relationship that will allow you to gain some insights into this trade-off of the two. And of course, our methods are not limited to these 3 or 4 examples that I'm showing at the moment. These are can be applied to very many different problems, and I see a lot of potential, for example, in the design of flexible manufacturing systems, also in warehouse configurations. We are currently working with a company who wants to integrate to look at an integrated problem that concerns the routing and the warehouse configuration. So if you think about the number of docks that you want to open at the warehouse and the number of vehicles and the vehicle routes that you then have from departing from this warehouse and the time that is needed in order to load the vehicles, then there is a clear trade-off relationship between the number of docks and the number of vehicles that you employ, and there you can also see this is nice trade-offs, and this gives further insights in how to plan the warehouses. And of course there are applications in production scheduling and many more. Okay, so what's our general approach? So we usually try to look at this from a kind of generic perspective, in the sense that if you can formulate the underlying logistics problem as a mixed interlinear program with 2 objectives at the moment. Mixed interlinear program means that you have linear constraints, linear objective functions, and the decision variables can be continuous or integer. In our case, they are usually binary, because many of the logistics problems that we model, they involve binary decisions. For example, opening a distribution center or not would be a binary decision, or using an arc in a route or not is also a binary decision that we can model. And then we try to use or develop or further develop our generic optimization algorithms and framework, and then we integrate tailored components in order to better solve the individual problem, but we also try to push our generic tools to be even better suited for solving any problem that can be modeled in this way. And you have seen before that you can either solve problems to optimality, or you can use approximative methods that we also call heuristics or meta-heuristics in order to solve the problems. And our current focus is clearly on trying to push the frontiers in exact methods. So we want to know the true optimal set of trade-off solutions and not only an approximation. But what I can already say here is that all our methods that we develop, usually they can be easily turned into heuristics in the way that you can just specify, for example, a time limit and return the solutions that have been found until then, and this will give you an approximative method. But this doesn't mean, of course, that heuristics are no longer needed, but we try to first solve them to optimality, the problems we look at, and then if this does not work, we turn to heuristics. Yeah, and today the problem I would like to show you for illustration purposes, it's a comparably simple problem. It's about the location of service facilities, and if you think about the current context, this could be about the location of testing centers for COVID-19 fast tests. And what we consider here are the opening costs for the facilities, the capacities at the facilities, a potential coverage radius of facilities. That means probably you will not drive to a testing center in Vienna if you're located in Linz, so you would probably only go to one that is close enough such that you can reach it within maybe, let's say, 20 minutes, maybe at most half an hour. And then, of course, you have the demand at the different population centers. So depending on how many people want to get tested, this demand varies. And this is also something I will talk about in a minute. And the considered objectives are, and you have on the one hand the opening costs of the facilities, and on the other hand you want to maximize the covered demand. So you want to cover as many people, or potentially cover as many people as possible with the budget that you have, of course. And on the other hand, it may not be clear how much you should invest into this opening facility. You can then nicely illustrate this trade-off between covered demand and opening costs. And here I also have an illustration of the problem. So if you look here, you see that this would be a potential local distribution center, and the blue circle here is the coverage radius. So anyone within the coverage radius, if the capacity allows as well, could be covered by this distribution center. And of course, if you only build one, you can probably only serve comparably few people, and the more you open, the more people or population centers can be covered by the facilities. But if you only build one facility, costs are low. If you build 3 facilities, costs are much higher, and you may have this overlap of coverage. So it may be better to choose maybe a further facility which has less overlap with this other facility. And now, of course, we can also put this into a mathematical model. You have seen a mathematical model before already. This is also a mixed integer linear program. What you see, we have the cost objective. So with each distribution center, there is associated a certain cost, and you have a decision variable that tells you if you open the distribution center or not. And on the other hand, you now see I minimize, because it's much nicer and easier to illustrate if you have 2 objective functions which go into the same direction. We minimize the negative covered demand, which is the same as maximizing the covered demand, and the covered demand is stored in this variable uj, which we sum up overall covered demand values for the different centers. And here we have a number of constraints. So we have to determine the provided coverage. We have to make sure that the capacity limitations are not exceeded. We have to make sure that only open distribution centers can be used to cover demand, and we do not want to have double coverage. Since we maximize the covered demand, we could, for example, if we do not have this constraint, we could assign some population of a population center more than once, and then we would double cover some of the demand, and this would artificially increase our covered demand figures, but this is of course something we do not want to have. And then we have the assignment, which can be fractional in our case. So we may have half a population center. So half of the population or the demand of one population center is covered by one facility and the other half by another one. If you look at this problem from a very aggregated level, then this is usually also reasonable to assume. And of course, we have the binary decision variables that decide on whether a facility is opened or not. And now we do not want to keep it too simple. We also want to consider the fact that demand is something that we don't know beforehand. If you think about the future, it's quite stochastic in the sense that it's unclear how many people will want to get tested, will want to get a vaccine, will actually be affected by a disaster if you think about a disaster relief setting. Therefore, we decided to also include this stochastic aspect into our demand figures. And I will show you now how we can include this into our model in a realistic or approachable way such that we can still solve the model. What we do is we use scenario sampling. This means that we have a probability distribution for our demand figures, and we use sampling to draw random samples in order to produce scenarios. And the more scenarios we have, the better we approximate, of course, our probability distribution. But we can start with a few scenarios and then increase and check if it still makes sense to increase the number of scenarios to better approximate. And if you think of a scenario, then you have the different population centers, are the different scenarios. You have 1, 2, 3, 4, 5 scenarios, and here you have the demand at demand point 1, demand point 2, demand point 3, and so on. And depending on how many scenarios you consider, the solution will be more or less accurate, but usually it's a good approximation of the underlying probability distribution if you consider a certain number of samples. And this then goes into the model in the following way. Instead of having now decision variables without this scenario index, we now add the scenario index to all decisions which can be postponed to the time when we actually take the decision. So what you see here is that the decision on opening a potential distribution center or not is something we have to decide now, and all other decision variables where we decide on how we assign the population to these open distribution centers, these can be decided once we actually know the realization of our uncertain demand. This means we have for each scenario a separate set of decision variables regarding the demand that is covered and regarding the assignment, the kind of assignment variable. And then in the objective function, we average over all the scenarios that we have, and we assume that we have n scenarios in our setting. And now this makes the model, of course, a bit more difficult to solve, because we multiply the number of decision variables which are linked to scenarios by the number of scenarios, and therefore the model becomes larger and larger, and sometimes it makes sense to consider like 500, 1000, even more scenarios, and then you need something that is more efficient than just trying to solve this model directly with some of our solution methods. And what can be done in this case is you can use a decomposition approach, which is also known as Bender's decomposition, or in the stochastic optimization domain as the L-shaped method. It has been introduced in 1969, so it's quite an old method, but it's still widely in use, and it allows to decompose the problem into a master problem where we have the decisions that we have to take here and now, which are part of the master problem, so the opening decision, and then you have one subproblem per scenario, and you include the information from the subproblems by means of so-called cutting planes. So you have an additional constraints that tell you how to push, into which direction to push the objective function value, which depends on the realization on the scenario information. And in our case, we have something that again simplifies the problem a little bit. So we have complete recourse. That means there exists a feasible solution for the second stage problem, no matter how we decide in the first stage. That means even if we cannot cover the complete population, this is feasible because we do not say that the complete population has to be covered or that the complete demand has to be covered. So even if you only open one distribution center and we can only cover parts of the population, then the second stage solution, which is the one where in each scenario we decide which population center will now be covered by this open distribution center, is a feasible solution even if we cannot cover everyone. Yeah, and this is what the master linear program looks like. We have here a bound on our theta. Theta is our new variable for the second objective function, and then we have optimality cuts which are generated iteratively over time, and we have the decision variable on the opening of the distribution centers, which are 0 or 1. So again, theta represents the second stage objective function or objective, and we solve the master problem. Then we check if the solution is optimal. There is an optimality condition. That means if my theta value is correctly estimated already, then I am done. Then I have a complete solution that is optimal. If my theta, for example, overestimates the covered demand or underestimates the negative covered demand, then I add an optimality cut that makes sure that theta is pushed into the direction where it should be. And how do we actually generate these cuts? We generate the cuts in the following way. So we look at our at our subproblem, which is one per scenario. So this is the problem where we transfer the information from the master problem, which distribution center should be opened or not. So these are the blue variables here. They are already set to 0 or 1. And using this information, we solve this subproblem for each scenario. Then this gives us what the objective function value for this scenario should be. And this can be used in order to include this information into the master problem. But there's a bit more of technique involved, let's say. So if you're from the linear programming domain, you know that every linear program has a dual problem, and that means that constraints are flipped to variables, and variables that are variables in the primary problem are flipped to constraints in the dual problem. And so we have here dual variables for each of our constraints, and we can use this dual information in order to construct our optimality cut. So the optimality cut, I will not go into the details, but you have to believe me now that this is correct. The optimality cut is in the following form, where you have, it's only based again on the set J variables which are in the first stage, so none of the variables appear which are in this problem, and we retrieve the dual variable values in order to write this cut in the form that even if you have a different solution that opens different distribution centers, it will be a valid cut or a valid bound on our theta value, which approximates the second objective function. Okay, and now how do we treat the bi-objective nature of the problem? So we now have a problem where it makes sense to include cuts in the way that we do not solve the complete problem immediately, but we add information from subproblems in terms of cutting planes. And before we started to work on this problem, we had developed a bi-objective branch and bound framework, which is a tree search. I will show you a picture in 1 or 2 minutes how it works. And it relies on, as if you're familiar with branch and bound, but I will repeat the idea on the next slide, that you have bounds and you have branches. It's also sometimes called divide and conquer, this idea. And in the single objective domain, usually a bound is a single numerical value, but in our multi-objective setting, a bound is no longer one value, but it's a set of points. And we have a lower bound set and we have an upper bound set, and the lower bound set gives us an indication in each node how good we can at best be, like in the single objective domain. And we have an upper bound set that consists of all non-dominated, potentially optimal solutions that we have found so far. And of course, we can use some heuristic procedures in order to provide us with an initial upper bound set in order not to start with an empty upper bound set. And every time we find a feasible solution, we check if it is non-dominated, and if yes, then we add it to this current upper bound set. And our key idea here is that the key ingredient to our bi-objective branch and bound is the way we use the lower and the upper bound set in order to derive a branching rule that is only possible in bi-objective optimization. And here, just a quick repetition for all those who are not directly from the area. So branch and bound, you usually start by solving the linear relaxation at the root node of your original problem. So you remove all integer or binary requirements from the variables, then you compute the bounds, then you find some variables which are not integer or binary as they should be, and you decide to branch on one of the variables, for example. Then you get two new nodes, where on the one you say that the variable should be, for example, if it's binary 0 on this side and 1 on the other side, then this gives you a new problem with an additional constraint that you solve again, and you get a bound, and you proceed in this way throughout the branch and bound tree. And whenever you find an integer solution somewhere that respects all integer and binary requirements, then this gives you a valid solution to your original problem. And whenever one of the bounds is worse than this incumbent solution, as you call it, has been found, then you can remove this branch of the tree from further consideration, because the bound indicates how good you can, in the best possible way, a solution in the best possible setting, a solution in this tree can be. And now the key difference to the single objective setting where you compare numerical values. So you have a numerical value for an incumbent solution, you have one numerical value for each of the nodes in terms of a bound. Now we have this additional complexity in biobjective optimization that we do not look at single values, but we look at sets and node sets in the set, and we call them bound sets. And I will now show you what I mean by this. So here you see, for example, these black dots are the potential non-dominated solutions you have found so far. So this could be potentially optimal solutions from your trade-off set, but you have not finished your branch and bound algorithm yet, so you don't know that yet. And then you are in a certain node and you compute the lower bound set. And this lower bound set then is this continuous, this line here, or this lower left boundary of the convex hull of all of the feasible solutions, of the image of the feasible solutions in objective space. And now what you see here is that some parts of this lower bound sets, they are already dominated by an upper bound point here. So here this gray area is the region that is dominated by upper bound points, and only the dotted white regions are actually the regions where you may still find better solutions if you find integer solutions. And our key idea here that we use in the branch and bound is that we use this for branching. So we do not only use decision space branching in the sense that we branch on variables, but we also branch on in the objective space in the way that we create node problems that relate to these white dotted areas, and we try to find only solutions in these areas. So in this case, we could, for example, construct 3 nodes, one that gets this area, one that gets this area, and one that gets, for example, this area here. Okay, and this is our idea in the branch and bound algorithm that we developed in the past years. And now we have this additional aspect that lower bound sets, this is something that, like in the single objective case, you want to have as tight as possible. So you want to have a lower bound set that is as close as possible to the actual integer optimal solution. And because the smaller the gap, the sooner you can also prune nodes from your branch and bound tree. And this is related to our cutting plane idea, to cutting planes, because whenever you add a cut in the single objective case, usually your lower bound gets tighter. And we want to use this idea in multi-objective optimization, and this means that cuts result in, if you add cuts, then you get a tighter lower bound set. And in order to understand this idea better and how we use it, I will briefly explain how the lower bound set generation works. So basically, in each node, we start by computing the extreme points in the linearization. So we optimize one objective, then we optimize the other objective, then we get these 2 points. And then we try to find, then this gives us a line between these 2 points. And then we try to optimize in the direction that is perpendicular to this line. And then we get a new point usually, for example, this one. And this is then our current lower bound set at this iteration would consist of this. And then we try to check if there's an additional point here or if there's an additional point here. And whenever we do not find any additional points, then this segment is part of our lower bound set. If we find an additional point, then we add the point, and we again try to check if there are additional points that need to be considered, and then we only stop if we find that there is no additional point. And now we stick to this picture here. Let's assume that this is the new solution we have found in our lower bound set, and if we add cutting planes, then this will move this solution. So I will illustrate this first here. So if this is our lower bound set, if you transfer the idea of making the bound tighter to multi-objective optimization, then this would mean that you get a lower bound set that is shifted upwards if you minimize. And now, in the literature for single objective optimization, especially when you apply Bender's decomposition, then the literature suggests to only generate cuts at the root node and at integer solutions, because then they can be most effective. And how can we transfer this now to our setting? This would mean that, for example, these two solutions are maybe fractional solutions because it's the lower bound. We have relaxed our integrality requirements, but this red solution is now an integer solution. However, we don't know if both objective values have been correctly estimated because we have this Benders decomposition included in our model, in our solution approach. So we have to add the optimality cuts. And when we add the optimality cuts, this means that we may push this point upwards, and it may even cross this line of the previous of the line between these two points on in the lower bound set. And in this case, what we can do, or what we know, is that we can stop exploring this line further, because this push tells us that there is a parallel line to this one, which is based on our new stronger formulation using the cuts. And so what we can do is we can stop exploring here and say that this is actually our lower bound segment here, and if we had found additional solutions, we would just need to explore the other ones. And we have implemented this idea, and it works really well, so we can discard a lot of lower bound generation by using this idea, and this can be transferred to any problem where we have valid inequalities that can be integrated by means of cutting planes. So this gives us a tighter bound set. And now I think I still have a bit of time. I will just briefly motivate the other approach that can be used by looking at the multimodal car sharing problem. And here we added additional complexity by integrated time-dependent user preferences. So the problem we looked at here was we had one objective that we minimized the costs, and then we had the sum of the preference scores that we also minimized. We pay attention to the minimization because 1 is the best score and 10 is the worst score. And then we have constraints, so each user has to visit all tasks assigned to him. So if you think about a corporate setting where users have appointments outside, then we use a carpool in the company, and then we have to assign to the user a car, or tell him or she or her to ride by bike or to take public transports to move to an appointment and maybe between appointments. So we have to make sure that the cars that are used, that are shared over the day, that they start and end at the depot. We assume that driver exchange in a car is only possible at the depot, because otherwise you will have to make sure that people meet, and this can be very inefficient. And we also make sure that trips between depots are carried out by the same mode of transportation. And then so here is also maybe a more illustrative way of looking at this problem. Assume that there's a company where there are Anna, Noah, and Ella working for the company. Anna has preferences. She doesn't really like to drive by cars. She prefers biking, or maybe using public transportation. But it also depends a bit on the time of the day. So we also included this time-related aspect. In the morning, she prefers the bike, but during the day, maybe she prefers to ride by public transport. Then you have Noah. I think of Noah, somebody who is always with his or her with his bike. So this is the bike enthusiast, and even if riding is not possible at all, he prefers to take the car, but preferably not during rush hours. And then you have Ella. This is someone who is maybe a bit older already. She prefers definitely using the car even during rush hours. She prefers to be in the car in the traffic jam compared to being on a bike or maybe sitting in a full train when using public transportation. And this can then be included by assigning preference scores over the day for the different modes of transportation. So this would be Anna's preference scores, this would be Noah's preference scores, and you also have, of course, Ella's preference scores. I guess you can look you can guess what they look like. So car is very much preferred by her. And then we include this information into our model, and we try to also take into account in a separate objective function the sum over the preference scores for our solution, and then this gives us a nice trade-off between the two. So this could be now a potential solution. The orange part here is the part that is used where the car is used, and the blue one is Ella. The pink one is, let's check again if it's the correct name. It's Anna, and the blue one is Anna. The purple one or pink one is Noah, and the light blue ones, this is Ella, and Ella gets the car for the first half of the day, then she returns to the depot or to the office location, does some work at the office. Then in the afternoon she doesn't get the car, but she does her appointments by public transportation, and instead now Noah is getting the car for the rest of the day. So this would be an example for a solution. And you can now we used a bit of a different approach in order to get all trade-off solutions. We developed a MIP model, we developed valid inequalities, and then we developed a single objective branch and cut algorithm, and then we embedded these into the epsilon constraint scheme. And this is a way where you enumerate solutions from one side of the frontier to the other by incorporating what we call epsilon constraints. So we have the two options: either you develop a very efficient single objective method that you embed in a scheme like this would be a criterion space search method, or you directly work on branch and bound, where you work with lower and upper bound sets throughout the optimization run. And it depends a bit on the problem what works better. For many problems so far we have found that actually branch and bound is a very, very well working alternative to existing criterion space search methods. And now I'm almost at the end. So what I would like to show you in terms of results, and also maybe tell you why again it's important to look at the trade-off relationships. So here you see, of course, that the green here, this is a performance profile. So the further, the faster the line goes up and reaches 1, the better. Here our implementation where we use valid inequalities and incumbent cuts is the one that works best. So you see that the cutting plane idea helps. And then we have here some car sharing results. Here we have different models that we solve in the epsilon constraint scheme, and the model that incorporates all the different valid inequalities and a lot of knowledge of the problem in the single objective case, which is then transferred to implementing it in the epsilon constraint scheme, is the fastest and solves all instances. We also used a different criterion space search scheme in order to check if this would also work well, but it did not work well at all. And now the last slide, more or less, before I leave the room for Stephanie Kritzinger, is that why do I think that this is really important to do? Because we see a very often this picture. So here you have the preference scores. I remember that we minimize them, and we have the cost. And we see that with very, very little cost increase, you can actually improve the solution from a customer or from a user perspective. And the same holds very often in terms of CO2 emissions and so on. So only looking at optimizing costs is not enough, but you can find trade-off solutions where the cost increase is comparably low, but it results in a tremendous increase in the other objective that you consider in addition to costs. Okay, and then here is my summary. So we have efficient generic multi-objective frameworks available, and now the next step is that we want to also consider 3 objectives, and this is what we are currently working on at the moment. So thanks a lot, and now if there are any questions, I'm happy to answer them.
Thank you very much, Sophie, for this very interesting talk. So at least, and especially thank you for presenting the bi-objective optimization by including such a hot topic as the vaccine challenge, which is definitely coming up. So are there any questions by the audience? Please feel free to just ask or raise your hand.
Yeah, I would have a question for the test center problem, COVID test center problem that you presented. Do you have any recommendation? How would you generate these scenarios for the sampling approach?
It's not entirely, we are currently considering how to do that, because we have this problem we have been working on in the last years for disaster relief data, and we are now thinking about how to include this how to solve the problem that is connected to the testing centers, but we have not found a final solution yet, so I cannot give you an answer at the moment. We have just been discussing this morning, so I think there's no final answer I can give you, but probably will include some demographic aspects into how willing we think that people in a certain region are going to be regarding going to get tested.
And this is also what you did for the relief, for the disaster relief problems.
No, in the disaster relief problem was in a sense different, that the demand was determined by how severe the disaster would be. So this is something that you don't know in advance. You have some knowledge on what's the range of values or demands that may be resulting from a disaster. But you have some probabilities on how severe the disaster could hit in a certain region, and then you can estimate the probabilities and also the probability distributions. But this is a completely different perspective, because in our case here it would not be the severeness, let's say, of the pandemic, but maybe it could also be linked to the number of people infected in an area, and then this could maybe give an indication on or used in a probability distribution to determine how likely how many people will be likely to go to get the vaccine or to go to the testing center.
Okay, thanks.
Okay, so Sophie, thank you once again for your presentation. Due to the ongoing time, I think there are there any more questions? I do not see any more hands raised. If not, I would like to once again thank very much Margaretha Gansterer, Sophie Parragh and Stephanie Kritzinger for their very, very interesting talks. I think you've convinced all of us to do research in shared resources, in bioobjective optimization, and of course then also to bring these things into implementation. Thank you for your attendance to all of you, and have a nice further conference. Goodbye.
Thank you.
Thank you. Bye.
Thank you very much. Bye.